Hi, we are now going to study about elasticity and about deforming forces. Now, whenever we talk about forces, what is the first thing that comes to mind? Forces produce acceleration. So, suppose I had this object, this block of mass m on a smooth floor, and I exert a force like this 20 newtons. What will this block do? It is going to accelerate in that direction. So, we know that forces can accelerate objects. But is that the only thing that they can do? No. If you look at this rigid rod and I exert 20 Newton force like this and a 20 Newton force like that, well, the net force is zero, but these two forces produce a torque and therefore this rod is going to turn like this. So forces can make objects rotate. So we know this also. But suppose I had this rod and I had two forces pulling it in exactly the opposite direction, and unlike this case where the two forces are not in a straight line, here the two forces are in a straight line. Then we can say that these forces cancel. Well, there also we can say forces cancel as far as movement or acceleration is concerned. Whereas in this case, the forces cancel for both rotation as well as for linear motion. Okay? Now, why do we say that the forces cancel? Does it mean that there is no effect at all? No. They cancel as far as rotation and motion is concerned. But rigid bodies, which is what we have studied so far, they can only move or rotate. So, as long as we are studying rigid bodies or particles, we don't need to worry about any other effect of force except motion or rotation, right? Linear motion or rotation. But actually, all objects that we have around us, they are not rigid bodies, right? They are objects that are real bodies, and real objects will deform under forces. So if there are two forces pulling this object, well, it can get stretched a little bit. So if I take this object and I exert forces like this, and if this was a real object, right, any regular object, then because of these forces, this object will stretch a little bit. Now these forces, they are deforming the body. Deform basically means changing the shape or the size of the body. So these forces are called deformation forces or deforming forces. Okay, now deforming forces are just simply external forces that are going to change the shape of the body or the size of the body. Now, if I look at this example here, this is a rubber band that somebody is pulling. Well, the rubber band clearly gets stretched. It is getting deformed because of these external forces that are being applied. Now, that thing is a putty. Now, if you take this putty and you pull it, well, it is going to also get changed, right? It's going to change its shape. It's going to get stretched. Now, the difference between these two is that once I release the force here, the rubber band will come back to its original size, whereas that putty is not going to come back to its original size. Now, we call that plastic and we call this elastic. We are now going to look at the difference between elasticity and plasticity. Let us understand the difference between elasticity and plasticity by first looking at elastic materials. What is the first elastic material that's going to come to your mind? A rubber band. So here I have a rubber band, and if I exert forces on this rubber band, pulling it, what is going to happen? It's going to get stretched. So that means its size is changing. The rubber band is getting deformed because I'm exerting deforming forces on it, right? So when you exert forces, pulling forces, the rubber band gets deformed, it gets stretched. And what happens when I stop exerting these forces? It goes back to being its original size. So I pulled it, it expanded, I released it, it went back to its original size. Is the only thing that does this is rubber band? No. For example, if you take a woolen sweater, you can pull this woolen sweater, it will stretch. You release it, it will go back to being its original size. And here is another example, steel. Now, usually people don't think of steel as being elastic, but steel is definitely elastic. For example, if I have this steel scale and I exert a force, a deforming force, you can see that it's getting bent. And when I release it, what happens? It goes back, right? I pull, it is getting bent. I release, it goes back to being its original configuration, original shape and size. In fact, You can place this on a table, hold it, press it down and release. You see that it will come back very quickly, right? It will oscillate back and forth like that, and finally it will come back to its original position configuration. So what is the definition of an elastic material? Elastic materials are those that bounce back to their original shape and size when the deforming force is released. Okay, when you exert a deforming force, the size or the shape changes, but when you release that force, then it immediately comes back to its original configuration. That is an elastic material. What is then a plastic material? Well, a plastic material obviously doesn't come back to its original shape or size. Let us take the example of a candle. Now, candle is made of wax. So if I take this candle wax and I press, well, the shape of that whatever wax that you've got will obviously change. But when you release the force, will it go back? No, right? It will remain in the shape that it had got. When you pressed it, whatever shape it was in, when you release it, it will remain in that shape. Another example is this putty that you probably played with as a child. When you press it, it changes shape. When you release the force, it does not go back to its original shape. It remains in the new shape that it has got. Another very important example is mud clay. It is because we can exert a force and change its shape that people use this to make pots. But then you don't have to keep on exerting the force. When you release the force, what happens? It remains in the new shape. So that is why it's important when we are using this for making pottery, right? So what is a plastic material? A plastic material is the one which gets permanently deformed. What does the word permanently mean? When you're exerting the force, it gets deformed. But after you remove this deforming force, it remains in the new shape. It is permanently deformed. It doesn't get back to its original shape and size. Okay. Now, when we talked about elastic materials, we talked about the fact that when you remove the force, it comes back to its original position. But is that always true? Suppose I take this iron rod and I bend it. Well, I don't have the force required to bend it properly, but here you can see this strong fellow is bending this iron rod. If it is bent that much and you release, do you think it's going to come back? No, right? It will remain in this shape and size permanently. So this has now become plastic, right? It used to be an elastic rod, but if you exert too much force on it, then it becomes permanently deformed, so it becomes plastic. Another very nice example is a copper wire. Now this I can exert forces and show you. So here is a copper wire, okay? Now if I exert small forces and I release it, you can see it's coming back. Can you see that? For small forces, it is clearly elastic. But suppose I exert large forces. It's not coming back, right? Now it is plastic. So the same object was elastic for small forces, but has now become plastic for large forces. Another very interesting set of examples, glass or ceramic. Well, they are elastic. You may not even think of glass or ceramic as being elastic, but for small forces, they are elastic. They come back, bounce back. But if you exert a large enough force, what will happen? It will break. It won't come back, right? So now you have to keep in mind that even elastic materials, right, become plastic when too much force is applied on them. So I hope you have understood the difference between elastic and plastic materials. The question that comes up is, why are these elastic materials elastic? Why do they bounce back? Let us try and understand that now. Why are objects elastic? Most teachers and books will tell you it is because of interatomic forces. It is correct. But how exactly do interatomic forces lead to elasticity? That is not usually explained very clearly. To understand that really well, we have to go a little deeper and understand how interatomic forces bring about elasticity. Let us do that by looking at this steel cylinder. Steel is an elastic object. So this is a steel cylinder. It is made up of atoms. Okay. Now if I take this atom, it is surrounded by other atoms. Right? I have shown you one atom at the top, one at the bottom, one to the right, one to the left. But there are also atoms in front and back. I have not shown that. It doesn't matter. Now all these surrounding atoms, they exert forces on this atom at the center. Now every atom will feel forces from its surrounding atoms. What is the nature of these interatomic forces? Actually, if two atoms are at a particular distance, which we call as the equilibrium distance, no force is exerted by the atoms on each other. Okay, so force is zero. But if you bring them closer, right, that means it is less than the equilibrium distance, then the atoms push each other back to the equilibrium position. And if you basically increase the distance between the atoms, then the atoms pull each other back to the equilibrium position. Is there anything else that does this? At a particular distance, no force. You expand it, it pulls. You compress it, it pushes. Springs do this, right? So interatomic forces are like springs connecting atoms. So if the atoms get too close, then the spring is going to push the atoms away, and the atoms get too far, then it is going to pull them. But remember, there are no real springs connecting atoms. Interatomic forces are like springs connecting atoms. So we are modeling it like springs for us to understand it more easily. There are no springs. The force between the atoms is like spring force, just to understand this. Now, I am interested in pulling this steel cylinder up and down like this, right? This I am going to pull up and this part I am going to pull down. So vertical forces, since it's along the length, I am going to say longitudinal forces. So because we are pulling it longitudinally, it does not affect the distances in the perpendicular direction. Basically, the transverse springs are not affected. Since they are not affected, unnecessarily if you put the springs, there are obviously springs here and right? But if you put all of that, it is going to get very cumbersome and complicated. So let us remove these horizontal springs. So we'll only talk about the vertical springs, right? So if I connect all the atoms with now springs, this is the image I want you to remember. Now, please remember that there are also springs connecting in that direction horizontally. I'm just removing it for the sake of clarity. Now, because I'm pulling both sides, what is going to happen? This cylinder is going to get stretched. But cylinder gets stretched means what? These atoms don't get bigger, right? Atoms don't get stretched. The atoms move and therefore the interatomic distance increases. But now I've put springs there. So when the interatomic distance increases, that means the spring gets stretched. So all these springs are going to get stretched. The vertical springs are all going to get stretched. Okay. So, but you can see that there's much longer chain. So let me just put a few more here so that you can see that this chain represents that. Easier to understand. I want you to understand that because of this, right, deforming set of forces, the atoms are not getting stretched. The interatomic distance increases. So the springs get stretched. Now, this force actually is acting on what? On the steel cylinder. But what is a steel cylinder? Steel cylinder is just a bunch of atoms, nothing else. So this force is actually acting on these atoms. Now, I have shown 3 chains like this. Are there only 3 chains in a big cylinder like this? No, right? There are going to be trillions of chains. So this force is going to get split over trillions of chains. So that means each of those chains will get a small fraction of the force. If I only show 3, it will be like F by 3, F by 3, F by 3, but there are trillions. So it's going to be F by some n. So I'll call it small f. Now I want you to understand that this is a deforming external force. These are deforming external forces acting on this, acting on this. I'm taking one chain for us to focus on. Okay. Now, because of this force, that was the reason these atoms started moving in the first place, right? This force is the reason this atom actually moved from this position to that position. But this force is still there. So why doesn't it continue to move? Because now the spring has got stretched. And so when it gets stretched, what happens? It is going to pull it back. Right? The spring is going to pull this atom back. With how much force? With small f. That's why this atom stops continuing to move up. In the beginning it was moving up, but then it stops, right? When you pull, what is going to happen? It will expand. But then will it keep on expanding? No, right? It expands and stops expanding. Why does it stop? Because of this force. Now remember that this force is an external deforming force. We will soon see that this force is called restoring force. Well, at the atomic level, we'll call this the restoring force. This is basically trying to stop it from expanding. Okay. Actually, this force comes from this atom. There are no springs. I just showed you the spring to help you understand that it is expanding. If you think in terms of the spring will pull that, but it will also pull this. But you can also say that this atom is pulling that atom is pulling this atom, action reaction. Okay, you don't need the spring. So now you can ask the question, why isn't this atom now moving up? Because of this spring, right? Which effectively means this atom is pulling that atom down. Now this spring is stretched. It is going to pull that atom and is also going to pull this atom. Why isn't this atom going up? Because of this spring. And this spring is going to pull that also. And why is this not going up? Because of this spring, so it is going to pull it down. You see that it is important to understand this chain of atoms. Now, this atom is going to pull that atom, and if that didn't happen, this external deforming force would have made this atom go down. In the beginning, this force will make it go down, but because of this intratomic force or this spring force, this atom stops. Very important to understand this. Okay, now if I think about this layer of atoms, you see that if I look at this atom is pulling it down, right? The spring is pulling it down if you want, or this atom is pulling it down, same thing. So, but it's not, this spring will pull that, but this spring will pull that, this spring will pull that. Suppose I look at this layer, all these atoms are getting pulled down. Well, the atoms above will pull all of them up. I'm not interested in that. I'm interested in what is happening to these atoms because of these atoms. And what is happening to these atoms? Well, these atoms are going to pull these atoms up. Now, let us say I make a cut here. Well, not actual cut. I'm just imagining a cut like this. Okay, this is called a cross section. So I'm making a cut like this. So if I make a cut like this, you can imagine that this is one part of the cylinder, this is another part of the cylinder. Let us take these two cylinders and separate them out. Now, this part of the cylinder, there is this external deforming force pulling it up. This part of the cylinder, there is this external deforming force pulling it down. And if this is pulling this up, why can't it go up? Because this part of the cylinder is pulling this down here. You can see that, right? That is the restoring forces here. So what is happening? These forces, well, where are they coming from? They're coming from these atoms. But now these atoms belong here. So that means this portion of the cylinder is pulling that portion of the cylinder downwards. F, only 3, right? Why am I putting so many? I showed here 3 chains, but I told you there are trillions of chains. So this is to just tell you that there are lots of forces like this, small, tiny forces that are acting here. And similarly, these atoms which belong there, they are pulling these atoms up, right? These forces together are called restoring forces. Similarly, these forces are also called restoring forces. Those forces are called deforming forces. They are external forces, whereas restoring force is an internal force. Intratomic forces between one part of the object and another part of the object. Okay. Now, how much is the restoring force? Well, now that's a little tricky, but in many situations it's simple. Like for example, here I'm going to assume that we don't have to consider weight of the object. Okay? That makes things more complicated. And I'm going to assume that this object is in equilibrium. Okay? It remains permanently at rest, let's say. I'm pulling it, but it is not moving. No acceleration. So that means this portion also is in equilibrium. Now if it is in equilibrium, net force must be 0, but that force is F. So what will be the sum of all these forces? F. Similarly, what will be the sum of all these forces? This is F. So the sum of all those forces must be F. So the restoring forces must be F. This restoring force and this restoring force always equal because they are action reaction. But is this force equal to that force always? No. In this case, because it's in equilibrium and I ignored weight, these two forces are equal and opposite, right? But in general, these two need not be equal. Many questions you will find that they are equal, okay? Because usually we are going to consider objects in equilibrium. But please remember, it is a conditional statement. Because if this was accelerating, then that force minus this force will be m into a. So they won't be equal. So remember that here I have made certain assumptions about this being in equilibrium. So the restoring force is equal to F. Now, why am I emphasizing so much about restoring force? Because there are 2-3 important points about restoring force. If you do not have this restoring force, remember this was the deforming force, right? External force that was pulling this atom. This restoring force, well, this is part of the restoring force, right? This force is the one that is bringing it back, right? It is, if it was not there, this will keep going. this force will drag this layer of atoms permanently, keep on pulling it, which means effectively you are just pulling it away from the body, rest of the body. So it will drag the end layers of the atoms away if there was no restoring force. So very important, restoring force is what stops the object from elongating forever. The deforming forces make it elongate a little bit, but once it elongates, the springs get stretched, right? If you want to think of it that way, the springs get stretched. So that means restoring force comes into play, and the restoring force is what stops it from elongating any further. So that is very important. It elongates and stops at that particular elongation because of restoring force. And once you remove the applied forces, right? Once you remove the applied forces, that is the whole point about elasticity. It will come back. What brings it back? Restoring forces pulls the atoms back. How exactly do they pull them back? Let us understand that now. When the applied deforming forces are removed, the elastic object goes back to its original configuration. How exactly does this happen? Let us understand that by looking at these two identical steel cylinders. Both are made up of chains of atoms like this. This cylinder, I am not going to apply any deforming forces, whereas this cylinder, I am going to pull it with a force F that way and an F this way. Now, because of these two forces, what's going to happen? This cylinder is going to get stretched, right? So, what does that mean? That means the atoms are going to move like this and the interatomic distance is going to increase. Basically, you can imagine it as the springs connecting the atoms have all got elongated. Now, this force, right, the deforming force at the top, it is actually acting on this topmost layer of atoms. Now, that's why this topmost layer moved up. But why does it stop moving? Because this layer of atoms is now pulling it back. The spring is stretched. The spring force is pulling it back. You can think of it that way. Basically, interatomic forces, they are pulling it back. The sum of all this is the restoring force, right? So these forces stop these atoms from continuing to move up forever. Now what about here? This force, right, the deforming force is pulling the bottom layer of atoms down. So that's why they moved down originally. But then why did they stop moving? Because the spring is now pulling it back. So the restoring force is pulling it back. So the first thing that the restoring force does is to stop the object from elongating forever. These restoring forces are the reason that it elongates a little bit. That's how you get the restoring force. But after it elongates a little bit, it stops because the restoring force now prevents these atoms from moving any further. Of course, now when the spring here is stretched, it's not only pulling those atoms, it is also going to pull these atoms. So we know that. And similarly, this spring is going to pull that down and this up and so on. So we know that all of these atoms are going to have intratomic forces like this. Right? So all these forces, they are restoring forces, and similarly these forces are also restoring forces. Every layer, if you add up all the forces, they are the restoring forces. Okay, so we know this. Now, so long, no problem. You can see that these atoms are all in equilibrium because that force and this force cancels, that force and this force cancels, and so on. The topmost layer is in equilibrium because the external deforming force that we are applying there and the restoring forces, they cancel. But suppose I remove the deforming force. I am now going to remove the deforming force. What do you think is going to happen? Will it instantly come back? No. These springs are all stretched. Will all the restoring forces suddenly vanish? No. So at the instant you have removed the applied deforming forces, the springs are still stretched. Once you have stretched them, it takes some time for the springs to go back, right? So at this instant, the springs are still stretched. Okay, now the restoring forces, why are they coming up? Because the springs are stretched. So the springs are still stretched. So the restoring forces continue to pull. The deforming forces we have removed, but the restoring forces continue to pull. But if you look at these layer of atoms, up and down, well, the net force on this layer is 0. Net force on this layer is 0, 0. But if you look at the top layer, there are forces pulling it down, restoring forces pulling it down, but the deforming force that was there originally I have removed. So what is going to happen to the top layer? It is going to go down. And when it goes down, the intratomic distance has reduced. It has gone back to what it used to be originally. But that means the spring is no longer stretched. It is not going to pull. but it won't pull the top layer, it won't pull this layer either, right? The next layer either. Wait a minute, I'm talking about the top layer. Now the bottom layer, the deforming force has been removed. Now because you have removed this, what is going to happen? These forces are going to pull the bottom layer up. And so these springs now have gone back to their natural length. So there is no more restoring force between these two layers. Similarly, no more restoring force between those two layers. I want you to understand this carefully. When the atomic springs go back to their original lengths, the restoring force stops. Wait, it has only stopped here and there. It's still there, right? But now notice this layer of atom, right? Like this layer of atoms, right? It doesn't have any upward force. It only has this downward force. So what's going to happen? This is going to go down. And then what will happen? This layer will actually start going down. Similarly, if you start with this layer, it is going to go up. So all this will of course happen simultaneously. So basically you're going to have this object go back to its original configuration. Notice it was the restoring forces that brought it back to the original configuration. Okay, let us understand this carefully. So restoring force is the reason the object comes back to its original size and shape, original configuration. Because the moment you remove the deforming forces, the external deforming forces, the restoring forces don't suddenly vanish. They continue to act until the object goes back to its original configuration. Once that happens, once it comes back to the original configuration, the restoring force finally vanishes. Okay, of course, all this happens very quickly as soon as the applied force is removed, but it still takes a little bit of time. That's why it takes a little bit of time for it to come back to its original configuration. Okay, happens very quickly but comes back. Okay, now restoring force, I hope you have understood, is the cause of elasticity. Why do objects come back to their original configuration? Because of restoring force. Okay, keep this in mind. This is very important. So this is the fundamental cause of elasticity. So why are some objects plastic? Perfectly plastic materials. There are materials which will be partly plastic, partly elastic. So they will have some restoring force. But perfectly plastic materials don't have a restoring force. So that's why when the applied force is removed, they don't bounce back to their original configuration. They remain deformed. So I hope you have now understood what is the cause of elasticity and what is the cause of plasticity.